For those who have not taken an advanced general chemistry course, by which I either mean Chem 190 or Chem 120, then it's probably useful to have a quick little overview on what matters for kinetics for the purposes of organic chemistry and also reaction coordinate diagrams. So at the core, if you hear the word kinetics, what you need to think is rate. This is about the rate of a reaction. And so fundamentally, what you're going to have in all cases when you're thinking about kinetics is an interest in the rate of the reaction, and it's almost always going to be equals to some constant. So how fast the reaction goes depends on some constant times the concentration of at least one of the substrates. And I'm writing Lg in there because most often what we care about for organic chemistry, at least in the Chem 240 land, is substitution reactions. We care about specifically Sn1 and Sn2 type reactions. And then later we're going to care a little bit about the kinetics involved in elimination type reactions. But fundamentally, we're not going to be considering kinetics for the entire suite of reactions. We're more focused on Sn1, Sn2, E1, E2, because what you're eventually going to end up doing is differentiating different reaction types based on which one happens fastest, which one happens first. So anyway, what I've written here is actually the complete rate law for a substitution nucleophilic first order reaction, which basically means that one thing decomposes in the slow step and then other stuff happens later. And there are two interesting substitution reactions: a substitution nucleophilic first order and of course a substitution nucleophilic second order. And this will start almost the same way. The rate of the reaction depends on some constant times the concentration of the substrate itself times the concentration of the nucleophile involved in this reaction. Why does this work out this way? Well, fundamentally, in the one reaction, what happens is you have a substrate which just simply falls apart on its own in the slow step. That's the slow thing that happens. And then later, some fast steps happen. And so how fast the reaction goes depends only on how much substrate you have. The more substrate you have, the faster this reaction can go because the substrate is more likely to decompose. And then once it decomposes, something else can come in and react with it. Whereas what this is saying is when you're doing a second order reaction, the rate of the reaction depends on the concentration of both the substrate and the nucleophile present, because fundamentally they need to collide in that slow step. What causes this reaction to take place is an actual collision between the substrate and the nucleophile. No collision, no reaction. And so the more substrate you have, the more nucleophile you have, the more likely collisions are between them. And in both cases, you have a rate constant because not all collisions are necessarily going to lead to products. So these need to collide in the right way, they need to be oriented the right way, and so on and so forth. So that kind of factor ends up in those rate constants. The key idea for kinetics for the purposes of organic chemistry is in one case, the substrate just has to decompose on its own before anything else can happen. And in the other case, you actually need to have a collision. And now we have reaction coordinate diagrams, which are a weird little thing that again shows up in general chemistry, but really gets applied well in organic chemistry. And fundamentally, what we're doing here is we're measuring energy of reactants versus reaction coordinate, which is actually kind of this bogus dummy variable, but it basically allows us to graph energies in two dimensions in such a way as to sort of spread things out. And what's happening in both cases, Sn1 and Sn2, is that you have some reactants here, which I'm going to label as R, and they're going to some products here, which I'll label as P, and the reactants start at some energy, and the products are at some lower energy, which is why this reaction takes place. And then what happens along the way is, in the Sn2 case, those substrates simply collide, and that leads to the products. And so there are no intermediates along the way. This all happens in a single step, and there's one interesting spot, which is the transition state. At some point along the way, you've got some bonds half made and some bonds half broken, and that's what causes the reaction to take place. And that's the interesting spot. On the one side, you have just the reactants, on the other side, you have just the products, and in between, at the transition state, is something that's worth looking at. Meanwhile, in an Sn1 type reaction, what happens is the material has to decompose first, because that's what's going on there, but it will then probably settle in some low energy well, some intermediate, and by low energy, I mean relatively low energy. It's higher in energy than that starting material, but then eventually it goes on down to products as well. And much like the Sn2 reaction has a transition state, then every single one of these humps is also a transition state. But in addition to the two transition states in the Sn1 case, there's also an intermediate. And an intermediate is a stopping point on the mechanism. For organic chemists, the mechanism almost always is electron flow. So this happens, which then causes this other thing to happen, and so on. But for the purpose of someone who's interested in kinetics, what's interesting about the mechanism is this has to happen in individual discrete steps. And so for an organic chemist, I'm interested in what the electrons are doing that causes those discrete steps to happen. But someone who's interested in kinetics is interested in finding out, all right, so what happens in each step and what's the sequence of events and so on and so forth. If the reaction happens in more than one step, then there's going to be an intermediate, something that's relatively stable that sits around for at least some lifetime. However, the path from reactant to intermediate almost always goes through some transition state, which, as suggested by the name, is transitory. It happens very quickly, very rapidly. You don't stay there for very long. So you pass quickly through that hump, and then you hang out a little bit in this valley, you pass quickly through that hump, and eventually you're at products. Meanwhile, if you have an Sn2 type reaction, there are no intermediates. What happens is it just all happens at once. The slow step of this reaction is a collision, which obviously is transitory in nature, and that happens quickly. For kinetics purposes, what we're interested in doing is looking at how likely a collision is to take place and whether a single substrate is decomposing on its own or two things must collide in the slow step. And we're going to describe that in part with reaction coordinate diagrams, which basically show that this happens in a single step. There are no pauses along the way, and an Sn1 reaction happens in two steps. One step gets you to the intermediate, you hang out there for a little bit, and then it continues on down to products. This is what you need to know from Chem 120/Chem 190 for the purposes of substitution reactions, of course. Similar considerations will apply for elimination reactions.